I'd like to talk about the following three problems and one method to solve all three of them. So I want to use Vieta's theorem to solve all these problems, but these problems are all different. So it's not obvious how to use the Vieta's theorem in the first place. The first one is just an algebraic expression where we want to prove that the terms ABC have some kind of relation in the form of geometric sequence. And the second one is system of equations with three unknowns. And the difficulty is that this system of equations is not a linear one. So it has quadratic terms and cubic terms. And the last one is, this one is more or less obvious because the Vieta theorem is on polynomials and their roots. So it looks like you can have some initial guess. You can say that, oh, this is something on polynomials and I can try to using Vieta's theorem. But the idea is you can, if properly arranged, you can solve all three problems using Vieta's theorem. So let's start with the first one. So maybe before starting with the first one, we can go see what's the Vieta's theorem. So the most popular case that everybody knows is for quadratic equations. The general form of the quadratic equations is ax squared plus bx plus c. So the term a doesn't make any difference. Like if you are choosing the polynomials yourself, you can go with the monic polynomials and then say the polynomial is, the leading term is 1, so you are just scaling out everything. So in this video, we are going to use the monic polynomials only. So the roots of the polynomial, this quadratic polynomial, is just solving this quadratic equation. If we say that we have like two roots, x1 and x2, you can factorize it as x1, x minus x1, and x minus x2. So these two terms, this is just the fundamental algebra theorem. And then when you open the parentheses, you are expected to get back this initial expression. So you open the parentheses and then your initial expression was x squared plus bx plus c. So these two are equal exactly. So we get the Vieta theorem by matching the coefficients, the coefficient in front of x, coefficient in front of x, and then coefficient, the free coefficient, that's this one. So they have to be equal. So if you write that out, we have the following system of equalities, which we call Vieta's theorem. The sum of roots x1 plus x2 is negative b, and the product of roots is c. And this idea can be easily generalized. So if we go to the case where we have like cubic equations, so we are going to, for all three problems in this video, they all have, so first two, they have like three unknowns. So probably we are going to use cubic version of Vieta's theorem. So let's write the cubic version. So the roots are the solutions of this cubic equation and x1, x3, x2, x3. And using the same logic from the previous for quadratic case, you can just factorize it as follows. And when you open the parentheses and then do the FOIL, there will be 8 terms, but you can combine like terms and then get a formula expression for sum of roots, which is negative b, so x1 plus x2. So sum of roots is the first quadratic term, and then you do the pairwise products and then sum, that's this term, and then the last term is just the product of all, which is negative minus d. So this is Vieta's theorem for the case of cubic polynomials. So we are going to use these to solve our three problems. So the first problem, we have three non-zero real numbers. So that's important. So the type of the numbers given in the problem is very important. So it's non-zero real. So at some point, probably you can use this information to justify some of your deductions. So let's choose a polynomial whose roots are ABC. So let's say Px is the following polynomial, a cubic polynomial, and it has 3 roots, A, B, C. So you can write it in this following polynomial form, but also you can write the equation in x minus a, x minus b, x minus c form, and then from there you can derive the Vieta's theorem. So by Vieta's theorem, you can do the sum of roots, the pairwise products. So sum of roots is going to be minus m, and pairwise products is going to be n, and the product of ABC is k. So what we want to do is use this polynomial to get some information about ABC, because this polynomial has roots ABC. So what we are going to do is maybe use this expression. So the first term is pairwise products, sum of pairwise products. That we have that expression n cubed, and then you can replace ABC with minus k and the sum with minus m. So that you end up with this expression n cubed is m cubed times k. So if you want to, going back to the polynomial, if you want to reduce the number of unknowns, you can replace k with n cubed over m cubed, because k is n over m cubed from here, right? So this means that we already used the given expression. So let me rewrite the polynomial as follows. Instead of k, you have n cubed over m cubed. So, and if I solve this equation, so if I solve this polynomial, set it to equal to 0, and then solve this equation, I'll have 3 numbers, a, b, c, the roots of this equation. But I can ignore the ABC for a moment and try to solve this cubic equation in this form. Like, for example, I can say multiply both sides. So get rid of this m cubed, the fraction. So if you multiply both sides by m cubed, you get this like m cubed here, m4, m cubed, and then this term. And then you can factorize this. So it's easy to note. So like the first one, so this one and this one, m cubed, these are cubic terms, and then these two, they have common terms. So here, m cubed x is the common term for the second and third one, and then these two are sum of cubes. Let's use the sum of cubes formula. If you use the sum of cubes formula for this one, you get mx plus n, the sum of two numbers, and product of the rest. So just recall the sum of cubes formula. So as you can see here, we have mx plus n as well. So if you factorize this, you can take out the mx plus n and factorize it. So the first term is mx plus n, and inside the parentheses we have the second quadratic term. So this is quadratic term, and this one is the first linear term. So we have been able to factorize the polynomial px, and so this from here, from first yellow parentheses, we can find the first root, and then from here we can find the second and third roots. So the first root is minus n over m. So this is equal to one of these three ABC. So we don't know which one, but one of them is minus n over m. And there are two others. So that's quadratic term. So there is x2 and x3. Do we want to find exactly what's x2 and x3? We can. So it's a quadratic term. You can use the discriminant formula and then find exactly what they are. But what we can do is, like, we can just focus on the question that they are being asked. ABC is a geometric sequence. So that's all we want to prove. And then from here, if you use for this quadratic term, use the Vieta's theorem again. The free term is n squared, the a is m squared, the product of x1 and x2 is n squared over m squared. So how do you prove that three numbers are geometric sequence? So if you know that idea, you are already there, because when so like these three x1, x3, x2, x3 are the permutation of ABC. These are the roots of px, and then these are the px. So which we don't know which one corresponds to the which one, but the idea is that we already have that x squared, the square of the first term is equal to product of x2 and x1. So this means, if you recall the properties of geometric sequences, when you have the product of two numbers is equal to square of third number, it means these three numbers make geometric sequence. So this kind of completes the proof. So this one says that these three numbers are geometric sequence. One of them is like square root of product of two others. So one thing to note here, so that completes the proof, but there is one thing to note. When we were solving the problem, we had this expression for k, which is n squared over m squared. So we just divided it here. So this is, if you are writing a complete solution to the problem, this is something that you should make a note. So the issue is that what if m is equal to 0? What if m is equal to 0? If m is equal to 0, then you wouldn't be able to divide n cubed by 0. And then all these upcoming steps would be invalid. So the solution doesn't work when m is equal to 0. So you have to make a note about that. So if m is equal to 0, just try to plug m here, 0. Then n is also 0. It makes n is equal to 0. So m and n are 0. And then your polynomial, so like if you make these two terms 0, polynomial becomes x cubed plus k. Just one cubic term and then one free term. And this polynomial should have three non-zero real roots. So because ABC are non-zero real numbers. And this equation, this polynomial cannot have this equation cannot have three non-zero real roots. So that's why the case when m is equal to 0 doesn't work. So it doesn't fit the definition of ABC. So we can ignore that case. M is not equal to 0, but you have to make a note about it, so that for the sake of completeness of the solution. So the second problem is a system of equations, and this system of equations has like one linear term with the first degrees, but the second term and the third term, they are quadratic, x squared, and this is cubic. So this makes the equation a little bit tricky, but what we are going to do is assume a polynomial again, the same way, same kind of polynomial. And the roots of this polynomial, let's imagine that the roots are x, y, z. So, and we will use Vieta's theorem. Using the Vieta's theorem, if I'm able to find m, n, k, the coefficient of the polynomial, so if I am able to exactly identify the polynomial, then I can solve this cubic equation instead of system, right? So that would be like rewriting the everything into one equation. So let's try to find m and k. So let's write the Vieta's theorem. What's the Vieta's theorem? It's product of roots, the pairwise product, sum of pairwise products, and the product. So that's the Vieta's theorem. And from here, x plus y plus z is 4, and that's minus m. So that gives me m is -4. So I know the value of m. How about the n and k? So in order to find n, I can use the square of sum of three numbers, x plus y plus z square is equal to x square y square z square plus 2 xy yz zx. And from here, I know some of the values. X plus y plus z is 4. So this part is 4 square. And here we have x square y square z square. That's 14. And then this part is, this is n here. So plus 2n. And this is a very simple equation. 16 is equal to 14 plus 2n. That gives me n is equal to 1. So 14 plus 2 is 16, 4 square. So I know what's n. So I know m, I know n. Now the last one is k. For k, I'm going to use another equation for cubic expressions. That's the following. X cubed, the sum of cubes of three numbers minus 3xyz can be factorized as follows. This is one of very important and very well-known identities. So from here we can do the similar thing. So we have 34 sum of cubes minus 3 times xyz is minus k. On the other side, x plus y plus z is 4. So 4 plus the 14 minus 1. So 14, and then this is minus 1 because n is 1. So again, this is very simple equation. We can just do simplification and find that k is 6. So we know m, we know n, we know k. So we can exactly write the value of the coefficients and exactly write what is the polynomial px, right? Px is the following polynomial. M is minus 4, n is 1, and k is 6. So now the question is to solve this equation, to find the roots of this polynomial. So that's another topic. That's another thing to study, I guess, finding roots of cubic polynomials. But if the finding roots of cubic polynomials in the case where you know that it has some kind of integer solutions, it's very easy. So that's something to check out from somewhere else, I guess. So I can rewrite the equation as follows. I will write the x as minus 5x plus 6x and factorize it. So the idea is just to factorize everything. Take out 6 here, so x plus 1. Here you can take out x, the common term, x squared minus 4x minus 5. You can factorize this quadratic term. That's x minus 1, x plus 1 minus x minus 5. Then you have x plus 1 as a common term. So just x plus 1 and then the rest. You can factorize this one as well. Then px is x plus 1, x minus 2, x minus 3. So that's the factorization of the original equation. And then from here, it's very obvious, like straightforward to find the roots. The roots are minus 1, 2, and 3. So these three numbers will give us the roots of this equation. Because the sum is 4, if you do the sum of squares, that gives 14, and sum of cubes should give you 34. So if we summarize, these three numbers, x, y, z, were the roots of this equation, this polynomial px, and we used Vieta's theorem to exactly identify that polynomial px. After that, just solve the polynomial px and find the roots to be minus 1, plus 2, and 3. So that completes the solution of this system. And the last one, is let a and b be two roots of the polynomial x4 plus x cubed minus 1. It's 4th degree polynomial. Prove that ab, the product of a and b, is a root of polynomial of this 6th degree polynomial. So the solution that I'm going to show, or solution, or the idea using the Vieta theorem may look a little bit unnatural, but one thing that should give you a hint that if you are solving this kind of problem in some kind of math contest or some kind of examination, then you should expect that it's some kind of well-constructed problem. It depends on some property. It's a derivative from some kind of property. It's not just a random problem. So it has very beautiful or interesting solution. That's like everything is exactly fit one each other. So it's not just like if you're doing some applied problem, you would not get something like this usually. So that's the idea. So the main assumption when you are doing some math contest or Olympiad problem solutions, the assumption is that there is a good solution. So that's the main assumption, right? So let's say that A, B, C, D are all roots of the fourth degree polynomial x4, this one. Because this is a fourth degree polynomial, it has 4 roots. We know first two, A and B, and I say like C, D are the other two. And let's write the Vieta theorem for this. So we have the sum is -1 because cubic term is 1. And then we don't have the square, x square or x terms. So pairwise sums, and the product of 3 and plus their sum is 0. And the sum of 4 roots, A, B, C, D, is -1. So that's Vieta theorem for this fourth degree polynomial. And I'm going to do the following. Let me introduce 4 more variables. S is A plus B, S prime is C plus D, P is AB, P prime is CD. So the reason for introducing these numbers is I want to have an expression where one of the variables is exactly equal to A times P. So that's P. So I'll try to get some relation in terms of P, because P is AB, right? So let me rewrite these 4 equations in this term. So the first one is going to be S plus S prime is -1. And then the last one, AB plus CD. AB, CD, the product of these two, P times P prime is -1. And then I can do some little bit algebraic tricks to figure out the rest, the second one. So like AB, we have CD, that's like P plus P prime, and then you can factorize the middle 4 terms. So that gives you P plus 1, and the middle terms are the product of these two only. And then the number 3, so like take the first two, take out AB, so CD is the inside the parentheses, and then for the other two you can do CD. So that gives me P times S prime plus P prime times S. So this is a new set of equations for me. So I'm not going to stop here. So I'll try to get rid of some of the variables. So like we have 4 unknowns. Let me try reduce number of unknowns. So what I'm going to do is get some expression, but that expression should be in terms of P only. So because P is AB. So what I'm going to do is just like get rid of primes. So P prime is -1 over P, and S prime is -1 minus S. So the first one and then the last one. And then I'll do these replacements in the second and third equations. So I'll be left with 2 equations, this one and this one. So like P plus, instead of P prime, I have -1 over P plus S. Instead of S prime, I have -1 minus S. And then for this one, P times S prime, replace this. p prime replaces p prime and s. So we have these two equations. Let's simplify these two equations. So like, let me go with the second one. And so the second equation is minus ps, s over p. So the second equation is this one. Let me find the s from here in terms of p and replace it to the first one. So that way I will have an expression that depends only on p. So this one, s is minus p squared plus 1, using this equation here. And if I replace it over here, the first equation, what I have is p minus 1 over p, these two, plus instead of s, I have the s here, minus 1, and again s, that's actually s. So that's the equation. That's the equation that depends only on p. So let me try to simplify this equation and then make it polynomial maybe. So if you subtract this one, the first two terms, and then open the parentheses here, you'll get this. And from here, you can do some little algebraic expression to get rid of the fractions and multiply both by p squared plus 1 square and then open the parentheses at the end. So I'll skip that step. At the end, you will end up with p6 plus p4 plus p3 minus p squared minus 1 is equal to 0. So basically this expression is this polynomial. And if you plug p to this polynomial, it turns out it will be 0, and which means the p is a root of this polynomial here. And at the same time, p is equal to ab. So that means if I plug ab into this expression, this polynomial, I'll get 0. So that makes ab a root of the polynomial, of this following polynomial. So that kind of completes the proof. So this was the third problem. So going back, so like we had 3 problems, and assuming that, so like looking at the problems, so there are several unknowns, and then if you assume that those unknowns are roots of some kind of polynomial, and then if you figure out the exact polynomial, then it turns out it's easier to work with polynomial rather than the system of equations or that algebraic expression or something else. So this idea is very one of the very commonly used tricks in contest math. You can try. So there are a lot of different problems, even for a system of equations or some algebraic expressions. So whenever you see similar problem, you can try to use Vieta's theorem and see if it makes your problem, if it makes your issue much easier.